Thank you. One last.
Recording in progress.
We'll start this maybe another one lecture on dosimetry, and lectures we will talk about measurements in dosimetry. And of course, main part of the material will be given by Dr. Romo. I mean, details of the measurements, but we cover just topics what we are using in our measurements. And first of all, we'll list all the methods that we use. Of course, we are using ionization method for dosimetry, scintillation, dosimetry, semiconductor dosimetry, luminescence, and Newton dosimetry. So the main element of the measuring device for registration of ionizing radiation is the detector. The properties of the detector, first of all, determine the technical characteristics of the device to the following. The ionization method is based on the measurement of ionization in the gas field detector. So with the ionization method, the ionization of molecules and atoms of a substance is measured. The method based on the use of charges, the electrical conductivity of gases. And next slide will show you that. Here are all the voltage characteristics, which already discussed in previous lectures. And here we are just remind some issues. So let's consider various modes of operation of ionization detectors. It has been established that the formation energy of one pair of ions is practically independent of the energy of the ionizing particle, mass, charge, and type of ionizing radiation. For most gases, this value is about 34 electron volts. Let's assume that the particle produces a certain amount of ionizations in the detector, corresponding to the initial electric charge Q0 in coulombs. Depending on the mode of operation, the charge can be partially or completely collected and can even be amplified. If the applied potential difference between the anode and cathode is too small, then the change will not be fully, the charge will not be fully collected. With the potential difference sufficient to collect all the ions, the charge Q equals to Q0 collected from the electrodes. This is the mode of operation of ionization chamber. With an event with even greater electric field strength, the primary electrons released by the detector particle acquire energy sufficient to produce ionization and release new electrons, secondary ones, which can in turn release the next generation, and so on. This process, called impact ionization, increases the number of ion pairs formed in the gas volume and the mechanism of gas amplification of the ionization effect of the detector radiation. Thus, the charge on the electrodes increases. Q becomes greater than Q0, and this is the mode of operation of gas discharge meters. The most significant difference between gas discharge counter and ionization chamber is the value of the field strength between the electrodes, on which the charge amplification coefficient K depends. This coefficient is numerically equal to the ratio of the number of ions that arrive to the collecting electrode to the total number of initially formed ions. Increasing the voltage further causes the final charge to be constant. Its value is maximum and doesn't depend on the energy of the ionizing particle. This is the area of self-discharge or Geiger-Müller counter-operation mode. A typical ionization detector is a gas-filled ionization chamber. I will not stop on this because the very thorough explanation was done by Dr. Kromov. Just tell the ionization chambers which determine the total ionization effect are called current chambers. In such chambers, the saturation current is proportional to the radiation dose rate. And the total amount of electricity generated over a certain time is proportional to the radiation dose during the same time. This determines the dramatic application of ionization chambers. But one thing should be discussed. For some purposes, some applications of dosimetry, it is important to know the dependence of the sensitivity of the ionization chamber. However, like any other detector on the energy of ionizing radiation, E is indexed down. The energy dependence of sensitivity is called a stroke with the rigidity. The sensitivity of a detector is understood as its response to a unit of measured value. For example, in the case of current ionization chambers, the sensitivity with the dose rate we call it I divided by dose rate. An ionization chamber can only be used to measure dose rate if its dose rate sensitivity is independent of the energy of the ionizing radiation. This is achieved by selecting the material of the chamber wall, usually air and gas, with the same values of the effective atomic number ZF, which for a complex substance is determined taking into account its composition. Such chambers are called homogeneous. A special case of a homogeneous chamber is an air equivalent chamber. The effective atomic number of the wall of which is denoted as VF and W related to the wall. It is equal to the effective atomic number of the air during the sensitive volume of the chamber. It should be noted that the effective atomic number of human tissues, approximately 7.4, is close to the effective atomic number of the air, 7.6. And therefore, air equivalent chambers are sometimes called tissue equivalent. A system of two electrodes separated by high quality insulation is charged by an external voltage source to an initial potential difference U0. It should be related in ionization chambers, which we call capacitor ionization chambers. In some works about principle of working. So the sensitivity of the capacitor chamber in terms of radiation dose, voltage divided by the voltage, is higher, is as higher as the larger the volume of the chamber, and the smaller is electric capacitance. Consider chambers have found wide application as some condenser chambers. Have found a wide application as the simplest individual dosimeter. The recharge of such dosimeters is carried out from a separate voltage source. The potential difference or the charge accumulated on the electrodes after irradiation is determined either on a separate measuring console or using a special electrometer mounted in the body of the dosimeter panel. Ionization detectors that use gas amplification of primary ionization are gas discharge counters. The use of the gas amplification mechanism makes it possible to sharply increase the sensitivity of the counters in comparison with ionization chambers. The scheme of switching and gas discharge counter is shown on the slide. When an ionizing particles passes through the sensitive volume of the detector, the current pulse appears in the circuit, which is recorded by change in voltage because the resistance R. The difference, the dependence of the count rate N is C, number of registered pulses per unit time on voltage Q. But the constant radiation intensity is called the counting characteristic of a dark discharge detector. The presence of the plateau in the counting characteristic determines experimentally indicates that the counter is in the Geiger-Müller mode. The longer the plateau and the smaller that its slope, the better that is the counter. Since Geiger-Müller counters register an independent discharge arising even from a single pair of ions formed in a sensitive volume. These counters are used mainly to measure the flux density of ionizing radiation or the activity of radionuclides. The applicability of one or another gas discharge counter for dosimetry of gamma radiation is determined by the dependence of sensitivity, N divided by voltage, on the energy of gamma radiation. The stronger this dependence, the less favorable the use of the counter. Conventional industrial meters have a significant sensitivity dependence on the energy of gamma radiation in the region of relatively low energy radiation, up to 600 kiloelectron volts. Only in a narrow range of energies is an accuracy sufficient for practice is a proportionality between the meter readings and the dose at the zero. To some extent, the energy dependence of the counter sensitivity can be reduced by using additional filters. However, it is more reliable to calibrate devices actually with counters by radiation of such as spectral composition, which is close to the measured in practice. Here's semiconductor dosimetry method. Inorganic and organic substances are used as scintillators for detecting ionizing radiation. According to the state of irrigation, scintillators are divided into solid, liquid, and gaseous. Okay, probably are you able to edit this? Okay. Because it is just repeating the effect of the problem. In general, the scintilation method is based on the registration of flashes of light where the current scintillators under the action of ionizing radiation. A scintillation dosimeter or counter consists of detectors that emits photons and of visible light under the action of radiation. A photoelectric multiplier that converts the light signals into the electric one, electronic recording devices, etc. The schematic diagram of the scintillation dosimeter is shown in this slide. And when gamma radiation interacts with the substance of the scintillator, electrons are formed which can absorb in the scintillator, create flashes of light or scintillations. Scintillation is a short-term of 10⁻⁹ to 10⁻⁴ seconds, light flash that occurs in a substance under the action of ionizing radiation. The light is directed to the light guide to the photocathode of the photoelectric multiplier. PMP. Each electron absorbed in the scintillator corresponds to a current pulse in the anode circuit of the power source. Therefore, both the average value of the anode current I and the number of current pulses per unit time, so NC, can be measured. In accordance with this, the current and counter modes of the scintillation detectors are distinguished. For the purpose of dosimetry and connection is established between the anode current I and current I or the counting rate of the NC and the absorbed dose rate in the air. This relationship is largely determined by the type of scintillator used. Of particular interest is the use of scintillation detectors for dosimetry of gamma radiation. In the current mode, the dependence of the detector sensitivity in terms of dose rate on the energy of gamma radiation is determined by the composition of the scintillation. Scintillators have an effective atomic number is lower than the air organic scintillators, or significantly higher for the case of inorganic scintillators. So they have a significant energy dependence of sensitivity in the energy range below 150 to 50 kV. A good way to compensate for the energy dependence of the detector sensitivity is to use a combined scintillator in which finally dispersed inorganic scintillator is incorporated into an organic one. In practice, this is realized by introducing 0.4% of zinc sulfide calculated by silver into the scintillating plastic, which equalizes the effective atomic numbers of the combined scintillator and air. The counter mode of operation for the scintillation detector is mainly used for the purposes of radiometry and spectrometry. The dependence curve of the detector sensitivity of the energy of gamma radiation doesn't have a horizontal section. Therefore, the uncompensated energy dependence of the sensitivity limits the use of scintillation detectors in the counter mode for dosimetry. And it limits its ability to use only by measuring radiation with a certain spectral propagation. Semiconductors are a wide class of substances characterized by electrical conductivity values in the range of 10 to 4, 10 to -10. Intermediate between an electrical conductivity of metals and dielectrics. The processes that occur during the ionization of a crystalline semiconductor detector can be explained on the basis of the band theory of crystals, according to which there are energy bands at allowed and forbidden values for electrons. It is customary to call the valence band the lower field band in which the electrons are in a bound state and cannot move freely. Conduction band is upper unfilled band in which the electrons have left the atom and can move freely. These bands are separated by an energy interval from the band gap. The band gap of semiconductors is approximately 3 electron volts, and hence the energy required to form an electric hole pair is the same order of magnitude, which is approximately 10 times lower than the average energy of formation of pair of ions in the gas. You remember that for air it is 34 electron volts. In addition, the density of the substance of a semiconductor detector is approximately 1,000 times higher than the density of the gas in the ionization chamber. Therefore, the absorbed energy under the same irradiation conditions in a semiconductor detector is several orders of magnitude greater than in a gas one. Thus, in the same radiation field, the sensitivity of a semiconductor detector will be several orders of magnitude higher than that of an ionization detector. So this is a part related to the bond method or the theory of semiconductors. So in semiconductors, due to the energy of thermal motion, the transition of electrons from the valence band to the conduction band is possible. In an ideal crystal, the concentration of electrons that appears in the conduction band due to thermal motion and will be equal to the concentration of holes, or not the speed, in the valence band. These charge carriers, which are able to move under the action of an electric field, determine the intrinsic conductivity of the semiconductor detector. In real semiconductors, there are always impurities that affect the electrical conductivity of the crystal. Because the number of carriers of electric charges increases. Impurities not only increase the total number of charge carriers, but can also change the ratio between the electron and hole concentrations. And the impurity atoms have one more valence electron than the crystal atom, then the extra electron can move around the crystal, creating n-type conduction. Impurities that provide a semiconductor with the electrons are called donors in impurities. And such semiconductors are called electron or n-type semiconductors. If you have the opposite situation, the impurity atoms have one electron less than the crystal atoms, then there is the possibility of moving electrons in the valence band, which turns out to be convenient to describe as a movement of a positively charged hole. Impurities that capture electrons are called acceptable, and such semiconductors are called hole or p-type semiconductors. The energy schemes of the intrinsic semiconductor, n-type and p-type semiconductors, in the representation of the intent theory of crystals are shown on this slide. Thus, the conductivity of intrinsic semiconductor detector is due to the transitions of electrons from the valence band to the conduction band. The conductivity of impurity conductor detectors to the n-type is due to the transitions of electrons from donor levels to the conduction band. And also the conductivity of the p-type is due to the transition of electrons to the receptor levels. In contrast to the ionization chamber, current flow to a semiconductor detector even in the absence of ionizing radiation. The presence of this background current in both intrinsic and impurity semiconductors makes them unsuitable for dosimetry purposes. But we have to solve this problem. In order to use a semiconductor as an ionizing radiation detector, it is necessary to create a layer depleted in charge carriers. It can be electrons or holes, then the ionizing particles. And then the ionizing particles, passing through this layer, form electron hole pairs in it by analogy with the ionization chamber. Under the action of an external electric field, charge carriers reach the electrodes. which is recorded by a current pulse. Created depleted layer of a semiconductor detector proceeds as follows. A layer of n-type substance, electronic conductivity, is deposited on the surface of a p-type semiconductor, which has photoconductivity. By diffusion, electrons from an n-type semiconductor will be introduced into a p-type semiconductor, and holes in them will go in the opposite direction. Similar reasoning can be carried out if a layer of p-type substance is deposited on an n-type semiconductor. After some time, an equilibrium state is established in which the resultant fluxes of electrons and holes are equal to zero. Under these conditions, a region is created in the semiconductor where the electrical resistance increases sharply and the electrical conductivity drops. This region with a low concentration of charge carriers is created. This region of the semiconductor, where the type of conductivity changes, for example, from electron to hole, or conversely, from the hole to electron, is called the transition region. In the transition region, the concentration of the equilibrium charge carriers is several orders of magnitude lower than in the rest of the bulk of the semiconductor. The carrier between the transition region is the main working region of a semiconductor detector. The absence of external voltage, the extent of the depleted layer is very small, on the order of magnitude by micrometer. However, the width of the depletion region increases when so-called reverse bias is applied to the p-n junction. It is the external voltage is connected to such a way that minus is applied to the p region and the plus to the n region. The switching circuit where semiconductor detector with the p-n junction is shown on the slide, and here layers p and n are separated by a transition region in which charge carriers are created under the action of ionizing radiation. These newly formed charge carriers are carried away by the electric field to the electrode in a fraction of a millisecond, microsecond. Silicon and germanium provided with the most convenient materials for semiconductor detectors with junction. The use of semiconductor detectors for measuring doses is limited by the noticeable dependence of the dose sensitivity on the radiation energy. There are some limitations. Instance, the essence of the method lies in the fact that charge carriers, electrons, and holes permanent luminescent dosimetry methods. The essence of this method lies in the fact that charge carriers, electrons, and holes formed in the phosphor under the action of ionizing radiation are localized in capture centers, as a result of which the absorbed energy is accumulated, which can then be released upon additional excitation. And that additional excitation can be caused either by feeding or by eliminating the phosphorus with a certain part of the light spectrum. The optics effects observed in this case can serve as a measure of the absorbed dose. Examples of such effects can be the actual luminescence, coloring of the phosphor, degradation of luminescence, luminescence which is non-irradiated phosphor. As a basis for the development of methods for dosimetry of ionizing radiation, two types of luminescence have been recognized: radiothermal luminescence and radiophosphor radiophotoluminescence. Currently, the next type of thermoluminescent detectors, for short TLD, are used. Single crystal of lithium fluoride activated by magnesium and titanium. Lithium fluoride single crystal activated with magnesium, phosphorus, and copper. Also, aluminum phosphate glasses activated with magnesium. Single crystal corundum or aluminum 2 oxygen 3, and magnesium borated polycrystals activated with dysprosium. Alkali halide compounds such as sodium chloride or lithium chloride, metastable glasses activated with silver are used as photoluminescence detectors. The radio thermoluminescence mechanism is based on the same band theory as semiconductors, of electronic states in solids. Materials that can be used as thermoluminescence detectors are solid insulators having a crystal lattice. According to the band theory, an electron in the ideal crystal cannot take on any energy values, where there are zones of allowed and forbidden energies. Usually, two adjacent energy bands are considered. The last few electrons, the B of valence band, and the first three C band of conduction, between which the band of forbidden energies F is located. You can see this in the picture. Conduction band, valence, forbidden is in the middle. Real crystals usually contain various structural defects. Or vacancies that cause local energy levels located in the band gap. To further create vacancies, some crystals are activated by impurities. Local levels of crystal lattice defects are filled with electrons if they lie in the lower part of the band gap, and free if they are located in the upper part. Under the action of ionizing radiation, equal amounts of positive and negative charge carriers are formed in a substance. In this case, as a result of the material photoelectric effect, electrons from the valence band can pass into the conduction band too, and then localized on the capture levels Z. It's a second dimension here. The places of holes semiconductors formed in the field band in place of knocked out electrons will be filled with electrons from the over levels. To release the energy of ionizing radiation accumulated in this substance, additional heating of crystal is required, as a result of which the electrons are released from the Z centers here. And then they combine with poles of the O centers. During recombination, the impurity atom on which the O centers was formed turns out to be in the excited state, which almost instantly passes into the ground state with the emission of the light quantum transition 4. The resulting glow is called thermoluminescence. The thermoluminescence spectrum is determined by the type of activator initially incorporated into the crystal. A distinctive feature of the luminescence is the distraction during heating of the centers created under the action of ionizing radiation. Under the action of ionizing radiation. So, therefore, after the measurement procedure, the thermoluminescent dosimeter loses information about the radiation dose and can be used for the next user. The glow of thermoluminescence serves as a measure of the dose of ionizing radiation absorbed in the detector. The measurement procedure for the dose using a TLD comes from the fact that the irradiated detector is heated at a given constant rate. And during heating, the dependence of the luminescence intensity J on the phosphorus temperature T is measured. Here of J and on the temperature T. The peaks on the curve. Let's make it biggest. Correspond to the release of electrons from certain capture levels located at different depths with respect to the conduction band. The shape of the TLC, thermoluminescence curve, is determined by the two competing processes: the thermal release of electrons and the depletion of levels. For practical purposes of the limiting, phosphorus with TLC are usually used in which the intensity of one main maximum is much higher than that one of others. So this actually is very big, and that one is like small. In this case, one of the two parameters of the thermoluminescence curve is determined. The total light sum released during the heating process, according to the integral method, or the maximum peak height, and the corresponding method is called Secant method. The integral method is more widely used. It is more accurate and less dependent on the technical parameters of the measuring installation, like heating rate, final temperature, etc. However, with the integral method or peak method, it is sorry. However, with the integral method, it is necessary to take into account fading, the decrease of detector readings over time. Fading is due to the presence of low temperature peaks in the phosphorus and the possibility of recombining of charged carriers even at room temperature. The fading correction is proportional to the ratio of the total area under the PLC. So there's part of it which is limited by low temperature peaks. The peak method is free from this shortcoming and has an advantage in measuring low doses. But this method is more sensitive to the heating regime or mode. For subsequent use, thermoluminescence detectors are again heated again at a high temperature up to the 400 degrees Celsius to completely free the residual capture centers. The radio photoluminescence mechanism. The radio photoluminescence mechanism is determined by the fact that ionizing radiation itself can create defects in the crystals. The same story like previous time, but in this case we will use different spectrum. The principle of operating it's here. The luminescence spectrum is due to the impurities initially incorporated into the phosphorus. The sensitivity of the luminescence is proportional to the concentration of the quantity centers and consequently to the radiation dose. The intensity of radio photoluminescence of the dosimeters as a rule initially increases linearly with increasing dose, then reaches the maximum and decreases with the further increased dose. And one more mode that we need is to measure dosimetry from newtons. All currently used neutron dosimeters, radiometers for operational measurements are based on the same physical principle. The registration of the thermal neutron flux density in the central part of the detector. Usually this part is enriched in boron 10, which has big cross section for the interaction with neutrons, especially thermal neutrons. Thermal neutrons at the center of the moderator are produced as a result of the moderation of neutrons of all energies. The size of the moderator is selected in such a way that the flux density of thermal neutrons generated from neutrons of any energy is proportional to the ambient dose equivalent rate of neutrons of the same energy. In order to improve this proportionality, the moderator is made combined. It consists of two spheres nested in each other. The large sphere has a diameter of 24 centimeters. The small one is 15 centimeters and is covered by carbon spin. To eliminate any influence of background neutrons. For such a neutron dosimeter with a combined moderator, the dependence of the sensitivity on the neutron energy quite well repeats the energy dependence of the ambient dose equivalent. They range from 10 kiloelectron volts and up to 5 megaelectron volts. Or we can say it converts almost the entire spectrum of neutrons arising from nuclear fission. Thermal neutrons are detected by a small detector that is inserted inside a smaller sphere. As such a detector, a scintillation or ionization detector containing boron is used. The nuclear reaction boron 10 and alpha is used. And the same detector can be used to measure the flux density of thermal neutrons only, or removed from the moderating spheres. So if only this one, it will measure thermal neutron flux density. The alien-1 sphere can measure the intermediate and fast neutron flux density. And then the alien additional sphere, and we measure directly the close equivalent rate. And then we can make a comparison with these approaches. In some cases, nevertheless, it may be necessary to measure the neutron spectrum. For example, when it is necessary to clarify the parameters of biological protection. For this, neutron dosimeters with a set of moderators in the form of spheres of various diameters are used. They are so-called Bonner's sphere. Such a spectrometer is called a multi-sphere spectrometer. Measurements of neutron spectrum makes it possible to more accurately estimate the ambient dose equivalent rate. Then, if the measurement will be performed using a dosimeter radiograph. And afterwards, albedo neutron dosimeters are based on the moderating and scattering properties of the human body. When a person is in the field of neutrons, his body, due to the slowing down and scattering of incident neutrons, it becomes, as it were, a source of thermal neutrons. The neutrons emitted by the human body are recorded by the albedo dosimeter. The albedo value is a ratio of the lumens of particles of backscattered radiation to the equivalence of incident particles. The principle of the method is that the individual neutron dose equivalent h with index p, okay, is estimated according to the readings of the dosimeter located on the human body, which reacts as a backscattered, which reacts to backscattered radiation. In practice, thermal-instance dosimeters selectively sensitive to thermal neutrons are widely used for these purposes. As a rule, two dosimeters are used simultaneously, one of which is made of a substance with a high content of lithium-6 and has a large cross-section for interaction with these thermal neutrons. The other one is made of a substance which is enriched with lithium-7. Both of these dosimeters are equally sensitive to photons and beta radiation, therefore, by the difference in the readings of these dosimeters, one can determine the individual neutron dose equivalent for neutrons. In order for the dosimeters to register only thermal neutrons emitted from body, they are shielded from the front side with cadmium or boron containing material. To increase the sensitivity to fast neutrons, the dosimeters use a polyethylene moderator. If the neutron spectrum where the dosimeter was calibrated differs from the neutron spectrum where the work is performed by personnel, then to make into account the difference in the neutron spectrum and determine the individual dose of neutrons, using an albedo dosimeter, a correction factor is introduced. We will calculating using the results of measurement of neutron spectrum at the places of work of the personnel. And in conclusion, so just a list of ionization, stimulation, semiconductor, and luminescence methods underline the operation of detectors for dosimetry, radiometric, and spectrometric equipment used at the nuclear power plants, in laboratories, medical centers, etc. System and hypothesis for monitoring the radiation situation and personal exposure. That's all for now for this lecture. These questions, it's all the time.
Thank you, Professor. There is many so interesting topics. So always say thank you to the professor. Okay, we're going to take 10 minutes for
Recording stopped.
10 minutos para el coffee break y luego regresamos a la segunda charla.